Have you ever wondered how we get electricity from an atom? Today, we're going to trace that exact journey, all the way from the tiny, powerful heart of an atom right to the outlet in your wall. Let's dive in and see how nuclear energy actually works. So let's start with a pretty mind-bending question. How is it possible that a tiny uranium pellet, something no bigger than the tip of your finger, can unleash the same amount of energy as literally tons and tons of coal? Well, the secret all comes down to something called energy density. It's just packed. A single one of these little pellets has the energy equivalent of thousands of gallons of oil or tons of coal. This incredible concentration of power is exactly why a nuclear plant can generate just a massive amount of electricity from a surprisingly small amount of fuel. You can power a whole city from a place with a relatively small footprint. Okay, so we know there's a ton of power in there. But how do we get it out? That brings us to our first section, the power inside atoms. We've got to unlock the energy that's in the nucleus. The key to all of this, the process that unlocks all that power, is called nuclear fission. And at its core, it's pretty straightforward. It's about splitting the center, the nucleus, of a really heavy atom, usually uranium-235. When that split happens, boom, it releases a tremendous amount of energy. And here's where it gets really clever. This process becomes a self-sustaining chain reaction. It all starts when one tiny particle, a neutron, zips over and hits a uranium atom. That impact makes the atom really unstable, and it splits apart. Now that split releases a burst of heat, which is what we want, but it also, crucially, releases a few new neutrons. And what do those do? They shoot off and hit other uranium atoms, which split, release heat, and release more neutrons, and so on and so on. It just keeps going, creating this continuous stream of energy. You know, a great way to picture this comes from our source material. It says, think of it like a tightly wound spring being suddenly released. When that atom splits, all of that energy that was holding it together is suddenly let go in the form of heat. It's not a fire, it's not a chemical burn, it's a physical release of just immense power. So, how do you take this tiny atomic process and scale it up to power millions of homes? Well, you do it inside a nuclear reactor, where the whole job is to split those atoms safely to generate a whole lot of heat. Now, it is absolutely crucial to understand one key difference here. A nuclear reactor is not a nuclear bomb, not even close. See, a reactor uses low-enriched fuel. We're talking only about 3 to 5% pure uranium to create a slow, controlled reaction that releases energy steadily over many, many years. A bomb, on the other hand, needs highly enriched fuel, over 90% pure, to create an instantaneous, uncontrolled explosion. They are fundamentally engineered for completely opposite purposes. And this quote just sums it up perfectly. It's like the difference between a campfire and an explosion. I mean, think about it. Both release energy, for sure, but one is designed to be slow, steady, and useful for warmth, while the other is designed for pure, instantaneous destruction. So, how do you keep such a powerful reaction under control? The key is something called control rods. You can think of them as sponges, basically, that just soak up those free-flying neutrons. By raising or lowering these rods into the reactor core, operators can speed up or slow down that chain reaction. It's almost like using a dimmer switch to turn the power up or down. All right, so we've made a massive amount of heat. The next big step in the journey is turning that heat into the electricity that we actually use every day. And you know what? This part is surprisingly old school. It works pretty much just like a coal or a gas plant. That intense heat from fission is used to boil water into really high-pressure steam. That steam then rushes past a giant fan, a turbine, making it spin like crazy. The spinning turbine is connected to a generator, and that generator is what converts motion into electricity. So really, the whole nuclear part is just a very, very sophisticated way to boil water. And what about those huge, iconic cooling towers you see at power plants? That's not smoke. That's a super common misconception. They're actually just releasing clean water vapor. It's basically a man-made cloud that's part of the cooling system. There's zero pollution coming out of those things. Of course, when you're dealing with this much power, you have an incredible responsibility. So let's talk about safety, which in the nuclear world is all built on a philosophy called defense in depth. And what that means is having multiple, redundant layers of protection, one inside the other. It's actually really interesting how they stack up. First, the fuel pellet itself is a ceramic. that's designed to trap radioactive material inside it. That pellet is then sealed inside a metal rod. Bunches of those rods are inside a massive, thick steel reactor vessel. And then, all of that is enclosed within a final, incredibly strong containment building. And just how strong is that final barrier? We're talking about 4 feet thick on average. The walls of that containment building are made of steel-reinforced concrete, and they're designed to withstand just about anything you can throw at them, from massive earthquakes to even an aircraft impact. The whole point is to make sure that whatever's inside stays inside. And what if something does go wrong? The reaction can be stopped almost instantly. There are automatic shutdown systems, sometimes called SCRAM systems, that can slam the control rods all the way in and halt the entire chain reaction in less than 2 seconds. So safety isn't just a rulebook, it's fundamentally built right into the physics and the engineering of the plant. All right, let's tackle a topic that gets a lot of attention: radioactive waste. And the key thing to remember here is that while the actual volume of waste is small, the responsibility for managing it is, well, huge. This quote really helps put the amount of high-level waste into perspective. All the used fuel from a person's lifetime electricity use would fit in a soda can. So while that material is definitely hazardous and has to be handled with extreme care, the actual amount of it produced is incredibly small compared to the sheer amount of clean energy you get out of it. And managing this waste is a very deliberate, multi-stage process. First, the used fuel rods are moved into a deep pool of water right there at the plant, where they cool down for several years. After that, they're transferred into these massive, secure steel and concrete containers called dry casks for long-term storage on-site. The ultimate goal, from every country with nuclear power, is permanent disposal deep, deep underground in a stable geological formation. And that brings us right back to the full journey. It all starts with the fission of a single atom to create heat. That heat boils water into steam. The steam creates motion by spinning a turbine. That motion drives a generator to create electricity. And finally, that electricity is sent out to the power grid and into our homes, from atom to outlet. It's a truly remarkable chain of energy conversion. So that kind of brings us to our final thought. Now that you know this whole incredible journey, from a tiny, invisible atom all the way to the light bulb in your room, how does that change your perspective on energy and on the amazing science that powers our modern world?